Here in this talk, I want to talk about some very simple observation. Okay, using the Weil-Petersson metric to construct some negatively curved metric on codiverse surfaces. So this is some joint web of Keung. Okay, and it's a simple one. Anyway, let me start with a Kähler manifold X. Okay, so here J is the J operator, okay, the complex structure on X, and the R is the curvature tensor. Okay, so let me just recall some notions of curvature. Okay, so here you take a pair of unit tangent vectors on the tangent space at a point of X. Then the sectional curvature is given by R UV Okay, it comes from some components of the curvature tensor. The holomorphic sectional curvature. So the sectional curvature is the usual curvature along the plane spanned by U and V. Then you have this holomorphic sectional curvature, which is given by R U J U J U U. Okay, so this is actually, of course, is just the sectional curvature along the Weil-2 plane spanned by U and J U. Okay, so in particular, holomorphic sectional curvature is a sectional curvature. Okay, sum of the sectional curvatures, and then you have this holomorphic bisectional curvatures is given by R, U, J, U, J, V, and V. Okay. So in particular, if U is equal to V, then you get back the holomorphic sectional curvature. But on the other hand, it's also equal to a sum of two sectional curvature spanned by U, V, and U, J, V. Okay. Anyway, so the holomorphic is called holomorphic bisectional curvature because it's a sum of two sectional curvatures essentially. Okay. So in particular, if the sectional curvature is negative, then the bisectional curvature is also negative because the bisectional curvature is a sum of two sectional curvatures. And remember, holomorphic sectional curvature is some part of the bisectional curvature. So again, if bisectional curvature is negative, then the holomorphic sectional curvature is negative. So the sectional curvature is sort of strongest, okay, among the three. Okay, bisectional curvature in the middle, and holomorphic sectional curvature the weakest. Okay, so let me not talk about So they are all so the holomorphic sectional curvature in particular is related to hyperbolicity of the manifold. Okay, but let me not talk about it here. So, okay. So let's look at some simple examples first. The case when dimension is 2, complex dimension 2. So here, the two simplest types of two-dimensional complex manifolds are like B2, okay, the unit ball, and C2 with the Poincare metric. So in this case, the sectional curvature is pinched between -4 and -1. It's quarter pinched. The bisectional curvature is pinched between -2 and -1. Okay, so it's half pinched. The holomorphic sectional curvature in this case is constant. It's -2. Okay. And then the next simplest example of the two-dimensional manifold is this bidisk B cross B, where you just equip it with the product of the Poincare metrics on each vector. Okay, so in this case, the sectional curvature is just semi-negative. Okay, it can be 0 along some tangent planes. Okay, some two-dimensional planes. Okay, and the bisectional curvature is also just semi-negative. Okay, now on the other hand, the holomorphic sectional curvature is strictly negative. It's pinched between -1 and -2. Okay, so we have these two very simple types of examples, okay, where for one, all the curvatures are strictly negative, but for the other, in general, you just get semi-negative curvature for bisectional curvature and sectional curvature. But although in this case, holomorphic sectional curvature is still negative. So in a sense, the holomorphic sectional curvature is negative. Is not very strong condition. Okay, as seen in this example. Okay, in fact, here you get the negativity of the sectional curvature just because each factor, the polychromatic is of negative curvature, but then on this product you take the sum of the metric, then it's negative. Okay, so to get negative holomorphic sectional curvature, what I want to say here is that in general it's not so difficult compared to bisectional curvature and sectional curvature. Okay, so of course, for the two examples that we have seen, the metrics, they are all invariant under the automorphism group of B2 and the bidisk. So if you take quotients, then you get the complex of manifolds with the same curvature conditions. Okay, say you take quotients of the unit ball or quotients of the bidisks, you get complex manifolds with, say, curvature semi-positive, semi-negative, but holomorphic sectional curvature negative. Okay, so so here I want to mention a result of Mostout and Seal, okay, in the early 80s, where they constructed an example of a compact Kähler surface, case again two-dimensional example, such that the sectional curvature is negative, but it's not a quotient of B2. Okay, so in fact, this was at the time this was the first example of a compact Kähler surface, okay, which is not a quotient of B2, but the sectional curvature is negative. And we call this numerical characterization of a Borg quotient, which says that a compact complex surface is a Borg quotient if and only if C1 squared is 3C2 is equal to 3C2. So in this case, if you compute the C1 squared and C2, compute the ratio, it turns out it's 852 over 298. Okay, so it's less than 3. Okay, so it's not a Borg quotient. Okay, once you compute these ratios of the Chern numbers. But what is interesting is that this is bigger than 2. Okay, it's between 2 and 3. In fact, the fact that it's bigger than 2 is not is really a must. Okay, because in general, one knows that if you have a compact Kähler surface with sectional curvature negative, then C1 squared has to be bigger than 2C2. Okay, and if you just want the bisectional curvature to be negative, then you can look for more topologically. You can try to look for more candidates, okay? Because there, bisectional curvature negative only will imply that C1 squared is bigger than C2. So yeah. Okay, so we have this example of negative sectional curvature, but not a Borg quotient. Okay, so the next is another possible source of examples of negative of manifolds with negative curvature are these Kodaira surfaces, okay, constructed by Kodaira in the 60s. So let me just recall the description, okay, here of this Kodaira surface. So here you take a Riemann surface R, okay, of genus G, okay, say bigger than or equal to 3, with fixed point free involution sigma. Okay, so sigma doesn't fix any points. And now you take a covering, okay, a m to the power 2g for a ramified covering, okay, S, okay, of R. Okay, so Q is the projection map from S to R, such that the Q star of H1 of SZ is image lies in the kernel of this. Okay, so it's torsion. And then you look at so on this R, on this S, you you look at this the product S cross R. Okay, you look at the graph of the graph of this map Q. Okay, so this is a one-dimensional subvariety in S cross R. Okay, given, so this is the graph of the map Q, and then you let this fixed point free involution act on delta, then you get another curve in S cross R, which are disjoint from delta. Okay, so you get delta and delta star, which are disjoint. Okay, they're disjoint because sigma is fixed point free. Okay, then okay, so now you take a m-fold branch cover of this product S cross R. Okay, you call it X. Okay, with a branching locus over the two curves. Okay, delta and delta star, and then you get this Kodaira surface. And then it's fiber over S. Okay, it's fiber over S, and such that the fiber, each fiber XS over a point in S is you can compute it easily. The genus is just m to the power 2g times g minus 1 plus 1, and you can also compute C1 square and C2. So they're given by by these expressions. Okay. So C1 square is, you can see, is bigger than 2C2 because this is 8 m to the power 2g times g minus 1 times mg minus 1. So it's twice that, but you have another factor, okay, another term here. So it's bigger than C1 square is bigger than 2C2, and but this term is less than this. So C1 square is less than 3C2. Okay. So one knows that so C1 square is between 2C2 and 3C2. So this actually provides you a candidate for trying to construct a calorimetric of negative sectional curvature. Okay, remember, if the sectional curvature is negative, then C1 square is bigger than 2C2. We won't be able to do it here. We will only settle for bisectional curvature. Okay. Yeah.
Are these surfaces provided this counterexample by compared by Osler and Q? Because it's C1 square less than 3, C2 cannot be the quotient of 4.
Right. Yeah. So both are not quotient. Both are not quotients of the ball. Yeah, both satisfy C1 square less than 3C2. Yeah, but both are non-ball quotients. Yeah. For Mostel's example, Mostel's examples as well as the Kodaira surface. Yeah, both are not ball quotients. If it's ball quotient, then you know it has sectional curvature negative. Right? Yeah.
Phi has single fiber.
No. This is smooth.
H1, H1 XS, TXS, what's the dimension?
Oh, you mean this one? Let me see.
Maybe this is using the
Yeah. Okay. So. And the point is that the Kodaira, you can also see that because of this branch covering, you know that this has it turns out that the Kodaira expansor map is injective. Okay, at each point. Okay, at each point in S. Here you treat this X as a vibration over S. Okay, and then it's not a trivial product because of this branching. So what happens is actually the Kodaira surface as a fiber space over S is such that the deformation is non-trivial. Okay, in fact, the Kodaira Spencer map is injective at each point. Okay, so you really have a deformation of the fiber space. Okay, the deformation of the Riemann surface. Okay, so and of course you can just define in general a Kodaira vibration surface as just one where the Kodaira Spencer map is always injective. Okay, so let's just record this. So here, at least for this talk, okay, a Kodaira vibration surface, or KFS, is a smooth complex surface emitting a Kodaira vibration, meaning that a fiber over some curve with smooth fibers, and such that the Kodaira Spencer map at each point in the base curve is non-zero. Okay, or is injective, in fact. Okay, so Kodaira surfaces are examples of Kodaira vibration surfaces. Okay. Okay. So here, what we are interested in here are the metrics on Kodaira surfaces and Kodaira vibration surfaces. Okay. So let me just recall some results. Okay. Chang's theorem, okay, in '89 says that every Kodaira vibration surface admits a Hermitian metric of negative holomorphic sectional curvature. Okay, and then later, Chai, well, actually, yeah, this slightly later, Chai, okay, now in Taiwan, okay, says that proof that every Kodaira vibration surface admits a Kähler metric of negative holomorphic sectional curvature. Okay, so you replace Hermitian by Kähler. Okay, so but as I say, to get negative holomorphic sectional curvature is not so difficult because here you have remember here you have a vibration, and you can more or less think of it as a product. Okay, just a product of two Riemann surfaces, and if the fiber has negative curvature, the base has negative curvature, then the product more or less has the product metric more or less is already of negative holomorphic sectional curvature, as as we have seen in the case of the bidiscs. Okay, or you take a product of Riemann surface. You take a trivial product of two Riemann surface. Take the Cartesian product. Already you would get negative holomorphic bisectional curvature, negative holomorphic sectional curvature. Okay, for the product metric. Yeah.
The restriction of the parametric theorem is just coincide with the parametric of the fiber.
For which one? For
the fiber Riemann surface has its own form.
Oh, you mean for these theorems? At least in this case, more or less. Yeah. In this case, I can't remember now, but not much difference. Yeah. You still, you basically still use the construction of the situation of like the product. Yeah. Very much like the case of the product. Yeah.
Not product.
No, but it's different. Yeah, you need to do something. But I want to say they are really not that much different from a product. So So in this sense, holomorphic sectional curvature, negative holomorphic sectional curvature is not so difficult to construct. Okay, more or less is. Yeah. Okay, so now okay, so just slightly moving ahead. Okay, so here I want to mention a thesis of a student at University of Hong Kong. Okay, Chui. Okay, so his thesis was directed by Mark. Okay, his theorem is this. Okay, here you take a codiral surface. So here these two are codiral vibration surfaces in the sense that it's general. Okay, not that constructed by codiral surface. But for Chui's thesis, he really just looked at codiral surface as that constructed by codiral, branching over a product. Okay. That surface. So now, if we suppose that each fiber in this codiral surface is non-hyperelliptic, okay, so make this assumption, then X admits a Kähler metric of negative holomorphic bisectional curvature. So this is the theorem, okay, of this thesis. Yeah. Huh?
I think that the assumption is always satisfied.
Is it?
I think so. Because the modular space of hyperbolic surfaces is affine. So this is constant. So if such a vibration with non-trivial Kodaira Spencer of this space, then it should be embedded into affine variety. So it's a contradiction. So I think.
Okay, but so it's for each fiber.
Yeah,
So you mean the whole space? You mean the whole space is embedded? No.
The base space.
Yeah. Here is the fiber.
You say that condition that each fiber is non-hyperbolic.
Right. Yeah. Yeah.
But at least one fiber should be smooth, right? All fibers are assumed to be.
No. In this case, all fibers are smooth. Yeah.
So smooth and
Yeah. The base is also smooth. Fiber is smooth. Yeah.
so
Yeah.
because the moduli map from S to
Mm-hmm.
we take with moduli space of hyperelliptic graph, and
Mhm.
the moduli space of hyperelliptic graph is I think affine.
Mm-hmm. Yes.
So if the vibration is non-trivial, this means and the Kodaira Spencer map is
So it doesn't intersect this locus.
yeah it's kind of divide that into it should,
Mm-hmm.
but
Yeah.
this provides a contradiction. So
Uh-huh.
there should be
Mm-hmm.
yeah, so every fiber should be non-hyperelliptic.
Because again,
Yes, so these assumptions automatically
Okay.
satisfy.
okay, yeah, okay, okay. So, but he stated as an assumption, I think, yeah. Okay, yeah. Anyway, so in this case, well, maybe this really we don't need case, but in any case, then in such case, then X admits a Kähler metric of negative bisectional curvature. Okay, he need this assumption really is. I can say a little bit why he need this assumption. Huh? What is the is somewhat between sectional curvature and holomorphic sectional curvature. It's yes, right. It's in the beginning. You can compute at the it's just given by R. So you pick a pair of unit tangent vectors, then it's given by R, U, J, U, J, U, J, V, and V. But turns out it's a sum of two sectional curvature. Yeah. So in particular, if the sectional curvature is negative, Then these two are negative, so this is negative. And holomorphic sectional curvature is a special case, okay, where U is equal to V. Yeah. Okay. Okay, so let me just go through a little bit the proof here of the construction of Chui. Okay, now okay, so here, so basically the way is to map this Godiva surface into the Jacobian. So here okay, we recall the principally polarized abelian varieties in correspondence with this Siegel upper half space. Okay, modeled by this SP2NZ. Okay, so this Hn is those complex, I forgot the symmetric, complex symmetric matrices whose imaginary part is positive. So you can construct a family of principally polarized abelian varieties. Okay, coming from this Cartesian product modeled by the SP2NZ. Okay, semi-direct product with z to the power 2n. Okay. And on this, on the universal cover, you can actually construct some canonical metric, so to speak. Okay? So what you do is on each fiber. Okay, so when you fix the tau, okay, then it's just given by z bar z, essentially z bar transpose z. So it's just Euclidean. Okay, just the Euclidean. The flat metric on the fiber, but then it varies, okay, when tau varies. And so this metric is such that on the fiber it's just the flat metric, but then you add this log determined imagined tau inverse. So this is well, you take the bar. So this is the Bradman metric on Hn. Okay, so we take this sum. Okay, so you can allow for a certain factor t here. Okay, it's not very important. Well, you can add this factor. So essentially, this is the so-called Kruger metric, where Kruger used this to prove well, it is in the case of compact quotient. This is a Hodge metric. Okay. So anyway, you have this metric. The point here is that along the fiber, the curvature of the curvature of the fiber is flat. Okay, so it's 0. But that is the curvature of the submanifold. So the curvature. You look at the curvature of the total space, and then you restrict it to the fiber. Then it's actually positive. Okay. So. Huh? Say again. Oh. The fiber is just this Cn. Yeah. So it's flat. But so the curvature of the submanifold is flat, but when you look at the curvature of the total space and then you restrict it to the submanifold, then it's actually positive. There are second fundamental forms, okay, non-trivial second fundamental form for each fiber torus, okay, of fiber abelian variety. Okay, so so now. So here, okay. So here, we recall we have this Godiva surface. Okay, so we have this fiber over S, and then you have this X. So you take the you let P be the projection from the Godiva surface to this product. Okay, so it's a finite cover with ramifications. Okay, delta and delta star. And now you let the gamma and gamma star to be the pullback of these two divisors on S cross R. Okay, so you have this gamma and gamma star in X. And now you look at this the map, okay, the Taurasi map from X to this AN, okay, where you just send each surface to its Jacobian. Okay. And then, so the remember here we want to construct a metric of negative bisectional curvature. So the let me just say briefly how it's constructed. It's constructed from pulling back of the this Cougar metric with an appropriate t, okay, from AN, okay, and pull it back to x, okay. So it's phi upper star of omega t. This is not negatively curved, okay. And now, so this basically takes care of the base direction, okay, so to speak. And then on the fiber, well, on the fiber you have some R, or rather you have a cover of R. So so here you look at this the Poincaré metric on yeah.
So you mean the phi is x to AN?
Yes.
For instance, the figure, for instance, phi.
Yeah.
So here, xs is the.
X is the fiber. X is the fiber over S.
Then jxs is
The Jacobian.
element of, is the element of AN? Or
It's an AN. Yeah, it's an
AN
AN.
is a pair, right?
Huh?
So AN is a pair. So how and
Yeah. AN. Yeah. It's the total space of this family of abelian varieties. So this is the AN. So this is a family of abelian varieties over a quotient of Hn. Yeah. Yeah. So here you have this Z to N. So this is a family of abelian varieties over a quotient of Hn. Huh? Jacobian. Yeah. C, yeah. Yeah. Okay. Yeah. So. Yeah. So here the basically the fiber direction is then sort of taken care of by the Poincaré metric on R, or the hyperbolic metric on R. Okay. You sort of again put it back. Okay. So all in all, this sort of will take care of. You will get a negative holomorphic bisectional curvature away from the tubular neighborhood of the ramifications. Okay. So in X minus some neighborhood of the gamma, the two branching divisors. And then what you do next is then you have to take care of the divisor, the neighborhood near the divisor. So for that you construct a certain singular form, and then which are concentrated near this neighborhood. Okay, so array is sort of small, and then you pull it back, and then you take the sum. You take the sum with the previous two. So this will in other words you have to take care of the neighborhood of this gamma and gamma star. Okay, and you can do that because because there is branching. Okay, otherwise, if you don't have a branching, then the tubular neighborhood of gamma and gamma star in X would just be a trivial product. Okay, would just be like this delta cross delta R. Okay, downstairs on S cross R. Okay, if you don't take the pullback. Okay, but because here when you take a pullback, there is a branching, so this allows you really to construct a metric which is concentrated near the ramifications and such that it's negatively curved. Okay, so I just want to say this distinguish. I mean, it's because here we are not looking at S cross R. We are looking at a branch cover of S cross R. That's what makes the computation works. Okay. Okay. So finally the design metric is this. Okay, it's phi upper star of omega t plus this omega r plus this h, which is sort of concentrated near the branching. Okay. So okay, let me just recall the condition that you need to assume the non-hyperellipticity is for this factor. Okay. If it's non-hyperelliptic, what you can make sure is that when you embed the curve in the Jacobian, then it will be embedded in such a way that for every point, the second fundamental form is non-trivial. So the flat metric on the Jacobian will restrict to a metric of negative curvature on the fiber. So that is the part where he needs the non-hyperellipticity of the fibers. Okay, so what I want to stay here is a simple observation. Okay, that actually every codial vibration surface admits a Kähler metric of negative bisectional curvature. Okay, in a very simple way. Okay, or in particular. Of course, every codial surface actually admit a Kähler metric of negative holomorphic bisectional curvature. And the way is to just a simple observation using the Weil-Petersson metric. Okay, so let's just recall, since here all the audiences are experts on Teichmüller spaces. So let me just go through this quickly. Okay, so let me denote the MGN to be the moduli space of Riemann surfaces of type Gn, okay, genus G with n punctures, and TGN, the corresponding Teichmüller space. For us, we are only interested in n equals 0 and 1, okay, and gamma Gn is the mapping class group, okay, of TGN, so that the moduli space is just the quotient of TGN by gamma Gn, and so every point in TGN corresponds to a punctual Riemann surface. So it's so Sx is just Sx bar is a compact Riemann surface of genus G minus p points. Okay. And remember the cotangent bundle of the TGN the cotangent space of TGN at each point corresponds to the holomorphic quadratic differentials with a simple pole, okay, at each of the punctures. And then if 2g minus 2% is positive, then each such punctual Riemann surface admits the complete hyperbolic metric rho. Okay. And then the cotangent space is in, I think this is, okay, maybe I should say the tangent space, okay, there should be no star here. So the tangent space of the Teichmüller space is in correspondence with the harmonic Beltrami differentials on the Riemann surface, okay, so so each harmonic Beltrami differential mu is just of the form phi bar over rho, okay, so rho is the metric, okay, phi is the quadratic differential, okay, so it's phi bar over rho, okay, and then mu will, so mu actually is sort of bounded and actually goes to 0 as z approaches the punctures. And rho is the hyperbolic metric. So this is like dz bar, dz bar. This is phi is like rho is like dz bar. Phi is of the degree dz bar, dz bar. So you cancel the dz bar, so you get like I mean yeah. Huh? Yeah, on Essex, yeah, yeah, right. So let me see. Okay, so phi bar is like a dz bar square. Rho is like DC tensor DC bar. You divide. You take the no. This is phi. So phi bar is like this bar. So you divide, and you divide. So and then you move this up. So it's like DC tensor. I think I better leave you to do it. Huh?
The last line of the slide contains.
Yeah, okay, see, yeah, it's of this cut, yeah, right, yeah. So it's a Bernoulli differential. Okay, so, okay, and then you can form the Weil-Petersson metric. Okay, so you take any two such harmonic Bernoulli differential. Its pairing is just given by the integral of mu1, mu2 bar times the hyperbolic metric on Sx. Okay. And the point is that this Weil-Petersson metric is invariant under the modular group, okay, and it's scalar. It's non-complete, but it's scalar. So so if you and what is also known is that this Weil-Petersson metric is of negative holomorphic bisectional curvature. Okay, you Wolpert wrote it down for the case when n is 0, okay, just for moduli space of compact Riemann surfaces, but it's not. It's easy to see that the more or less the same calculation will also show that even when there are punctures, the Weil-Petersson metric is still of negative bisectional curvature. And now by now you more or less should know how one can construct this map. This negative curved metric on the Kodaira vibration surface using this Weil-Petersson metric. Okay, so here what you do is you look at the diagram. Okay, so you have the Mg, the modular space of Riemann, compact Riemann surface of genus G, and then you have Mg1, and then you have this. Remember a Riemann surface in Mg1 is just a compact Riemann surface with a mark point. Okay, so and then you have this forgetful map. Okay, by forgetting the y, so you just get capital Y, little y sending to y. So you have this forgetful map. You forget the mark point, and you have a you can lift this forgetful map to the universal cover. So it's from TG1 to TG. So you have this F tilde. Okay, again the forgetful map, and and then these pi's are the quotient corresponding quotient map, and you have this this diagram being commutative, and each okay. So for this forgetful map F, the inverse image of each point here is just the corresponding Riemann surface modeled by the automorphism group of the surface. Okay, so for generic points, the inverse image of a point is just Sx. But then at some points where the automorphism group is not trivial, then the fiber is just this. Okay, and then, but if you lift this to the universal cover, then it's very nice. Okay, so let's recall this Bayes fiber space theorem, which says that on TG1 and TG, okay, the F tilde, the inverse image of F tilde for a point in TG is actually just H. Okay. Okay. This inverse image is just H, the upper half plane, and moreover, you have this short exact sequence of groups. Okay. This is gamma G1, the modular group for for Riemann surface of type G1, and this is the gamma G, and then the quotient phi G which fix the Riemann surface. Actually, they is isomorphic to the Riemann surface of isomorphic to the fundamental proof of a Riemann surface of genus G, and such that for each fiber, the quotient of each fiber modeled by this phi G, okay, which fix fix the point in TG. Okay, this quotient is just S of Y. Okay, so here, so on the universal cover, we have a very nice fiber space. Okay, each fiber is just H. Okay, and then you sort of take the quotient, and you get the SYs. Okay, and okay, so once you have that, then you can construct well, you don't really need to construct actually. You just okay. So now you take a Kodaira vibration surface, okay, and then you take this. You look at the classifying map, okay, of the so as a base space, okay, C, okay, you map it to the moduli space, okay, and then you better look at you better leave it to the universal cover, okay. So you may want to do it locally, but anyway, you just essentially just map this base curve to the tetramer space or the moduli space, and then you look at the corresponding, and then for each point in the Kodaira vibration surface, you look at the corresponding pair. Okay, so it's the fiber, so it's the Riemann surface. Okay, associated to pi x. Okay, pi is the vibration map. Okay. And then, so the point x, yeah, and then with this mark point x. Okay, so this corresponds to a point in MG1 or TG1. Okay, and then you just see that this gives you a map. Okay, from the Kodaira surface to MG1. At least locally, or you can leave it to the universal cover to TG1. And then you just, you can see easily that you get an immersion, okay? Because it's immersion along the base direction, because by assumption, you are looking at the Kodaira vibration surface. The Kodaira Spencer map is injective. And on the fiber, on the fiber is just the, you will call this Bayes' fiber theorem. Okay, actually you can just associate naturally the fiber with the fiber in Bayes' vibration theorem. Okay, so you get an immersion, and then and then, so finally, then you look at the Weil-Petersen metric on TG1, and then you sort of just restrict it to the Kodaira surface, or the Kodaira vibration surface. And then you restrict a Kähler metric of negative bisectional curvature to a submanifold locally. Then you get a Kähler metric of negative bisectional curvature. Okay, so this is really simple observation. Okay, since the I think I will just skip that you can generalize Volpat's construction here to see that the Weil-Petersen metric is of negative holomorphic bisectional curvature. Okay. The formulas are the same, and in the case of punctual Riemann surfaces, you just have to when you compute the Laplace, when you look at the decomposition, the spectral decomposition, of say this term, okay. This term is semi-negative, okay, and then this term is negative. This term is negative and is 0 only if mu I times mu j is 0, which again means mu I or mu j is 0, okay. So I think I will just skip this part, okay. Yeah. I mean the argument is the same as both parts. The only thing is when you look at the spectral decomposition for punctual Riemann surfaces, you have some terms arising from the continuous spectrum. But so it's more or less known to express here. Okay, so I think I will just stop here.